We are Senior Design Team 8, Handcycle Smart Trainer. Our advisor is Dr. Andrew Merriweather. The students on this team are Quinn Allman, David Brasharis, Joseph Davies, Andrew Iyer, and Matt Laverty. Our project sponsor is Dr. Jeffrey Rosenbluth. For this project, we worked with the Craig H. Nielsen Rehabilitation Hospital through the Technology, Recreation, Access, Independence Lifestyle Sports Program, or TRAILS. The TRAILS program is focused on allowing patients with limited use of their limbs the opportunity to do sports activities they would otherwise not be able to do, specifically sailing, skiing, and cycling. Our project was focused on constructing a smart handcycle trainer for the use of the TRAILS patients. Hand cycling is a popular form of exercise for people with spinal cord injuries. A hand cycle is a bicycle that is pedaled with hands instead of feet like a traditional bike. However, it is not always feasible to ride a hand cycle outside due to weather, like we had yesterday, with tons of snow or days where it's too hot. Spinal cord injury patients have poor thermoregulation, so being in extreme weather conditions is generally not advisable for them. Hand cycle trainers allow our users to get their exercise, even when the weather doesn't allow them to ride outside. There are a few problems with current handcycle trainers on the market today. Most are not designed with handcycles in mind, so they don't accommodate all the varying models of handcycles that exist. They are also difficult to set up for users with spinal cord injuries due to their limited hand dexterity. The riding experience is also not great on current trainers, as the resistance levels they can provide is limited and difficult to adjust. The goal of our project was to address these issues by making it easy to set up and use prototype that offers smart features that give the user a better and more dynamic riding experience.
Some basic constraints our project had for our design involved price, weight, and strength. We needed to keep the prototype under $500 to produce in order to be competitive with our other trainers on the market. The final design itself cost around $400 to produce, so it was within our target. We needed the design to be under 40 pounds, so it was somewhat portable. Our design came out at around 25 pounds, which we were very happy with. Finally, we needed it to be strong enough to support approximately 300 pounds, so it could be robust enough to support any rider and hand cycle. We were not able to obtain the exact maximum load our system could support, but it was able to support the rider and hand cycle load of 300 pounds we expected, and likely can go much higher. The most important things we wanted to design for were high functionality of the trainer and a high level of ease of use for our patients. We wanted the resistance mechanism to be automatically adjustable and able to simulate a similar level of effort as riding outside. We are able to keep the trainer very simple and easy to set up and programmed a phone app-like system to allow the users to adjust the resistance easily. We also incorporated pre-programmed courses as well as an SD card system to allow users to make their own courses if they wanted. We spent much of the first semester doing research and making initial designs in CAD to find the best ways to make our trainer. One of the best things we found during our research is something called the Scheiber model, which is a mathematical model that details how magnetic fields interact with respect to magnets and flywheel systems, which our design is. We wanted to better understand how magnetic systems worked in practice to compare them to the theoretical Scheiber model. So we constructed a prototype experiment that simulated riding on a hand cycle. We hooked up a high-tech motor to the prototype that allowed us to measure the torque, input voltage, RPMs, output torque. It measured everything. From that experiment, we were able to collect a large amount of data that proved beneficial throughout the design process, as it told us the peak torques and speeds we needed to design for, and told us how many magnets we would need and how large of a flywheel we would need for our design. We were also able to leverage the Scheiber model information and our own experimental data to construct a mathematical model that we used to construct our control system algorithm.
Our design incorporates ideas from existing trainer models while improving and emphasizing ways to make the trainer more accessible for our patients. The trainer has a basic frame with 2 rollers suspended between, a ramp at the front for hand cycle access, a flywheel for resistance, and 2 stability guide rails. The guide rails are adjustable for any trainer size or shape, and the resistance can be adjusted dynamically and discretely to any value the user desires. To address ease of use, we included friction lock clamps for the stability guide rails. This allows the user to simply open the friction lock with a lever and position the guide rails where they need for their hand cycle. The lever is ideal because it requires minimal grip strength to operate.
To address the dynamic resistance need, we implemented an eddy current brake to the system. We can control this resistance with a stepper motor that is attached to a series of magnets that can be moved closer to or further away from the flywheel. The flywheel that spins during operation generates a resistive torque when in the presence of a magnetic field. As the magnets move closer to the flywheel, the resistive torque increases and the resistance on the rider increases, giving them a harder ride. As the magnets move further away, the resistance lessens. In order to accurately control the resistance, we generated a mathematical model for the eddy current brake by using theoretical knowledge as well as gathering data with an experimental eddy brake setup. This was done to ensure we could simulate the range of resistive torques a rider would experience on the road. The model also shows the combined effect that the speed and the position of the magnets have on the eddy current brake. The control system that we implemented adjusts the resistance automatically during use. It adjusts based on the speed the rider is going and the workout mode they have selected. The workout modes have set trail inclines that are simulated. The user also has an option to put an SD card with trail data of real trails for increased immersion. An optical encoder is used to measure the speed which is run through the mathematical model. Based on the workout selected, the proper resistance is calculated and the corresponding magnet distance. This information is sent to the stepper motor to put the magnets in the right position. This feedback loop runs continuously to control the resistance.
The best features of this design are the variable resistance mechanism and the stability guide rail system. The variable resistance mechanism has a discrete resistance value that is checked continuously as the user rides, allowing for constant feedback and giving the most authentic ride possible. Our users will also be able to simulate riding any trail in the world, whether it be up and down their street or up and down Mount Everest. The stability guide rails are much easier to set up and use than current models. They have a straightforward friction lock that can be opened and closed with minimal hand force and dexterity. They're able to accommodate any hand cycle with ease. The things we would change or improve if we had more time are the phone app interface and adding some additional user features. The programming as a whole could have used more time to iron out the kinks and make sure everything is running as smoothly as we would like. We also would have liked to incorporate a fan that turns on or off depending on the user speed or resistance, and the ability for an incline adjustment to erase the front of the bike, which would add to the realism of the trainer and allow the user to feel even more like they are riding a bike up a mountain. Both are doable additions if there was a bit more time for this project. We would try to find a way to use different materials for the stability guide rails and side frame to reduce the weight of things and make the trainer more portable. Finally, the end goal for this project is to incorporate our trainer into live bike classes like Peloton or Zwift. We weren't quite able to get there this year, but it is a doable goal with the groundwork we have laid. We would also like to give a special thanks to our advisor, Dr. Merriweather, and our sponsor, Dr. Rosenbluth, and his team in the Craig H. Nielsen Rehabilitation Hospital, and the Trails Facility for all the support throughout the year.